All right. So this is my diagram of trying to get into Club Converge or being forced out the exit or not being let in at all. So what we've got here are a bunch of infinite series going, can I get into Club Converge? And the nth term test for divergence is the person at the door person at the velvet rope, who's deciding, you look good enough, and letting them in. Now, admittedly, often the person at the door goes on a bathroom break and everybody just runs in, or they fall asleep on the job. Because we often don't think about this test, we're always just kind of going straight into the foyer of Club Converge, but we're still not in yet because we're either going to be sent with a ticket for entrance to Club Converge, or we'll be given an exit ticket, and the test will give us these tickets. Now, as you enter Club Converge, you're going to notice some things. You're going to notice that there's this, I apologize for the Harry Potter reference, pureblood entrance and the muggle or mixed blood entrance to the tests for just plain being a harmonic series, the geometric series test, and the P series test. You can see the purebloods. Oh, and by the way, I put it in green for Slytherin because, yeah. Anyway, so right here you've got a pure geometric series where you have some first term multiplied by, I know Slytherins aren't all bad. I got schooled many, many years ago by a Slytherin who said that J.K. Rowling was very biased against Slytherins and needed to open up a little bit more to what is in there, and that evil comes from all areas. All right. So, then basically you've got the pure geometric series. You've got the pure P series. They can come in and get tested, and I see this is the little door they exit out of. Oh my goodness. Then we come to the muggle or mixed blood entrance. Oh dear. Okay. All right. If you go into this entrance, you likely are one of these characters. If you have addition or subtraction going on within the division, or maybe there's not division, but this right here is showing you've got addition, subtraction of stuff. You're likely going to need to come in here, and you may need to figure out which of these two tests you want to use, direct comparison or limit comparison. And as you walk in, you notice that one of the tests is right there at the direct comparison test desk. And that is somebody who has multiplication with sine. And someone who has multiplication with cosine also might be there as well. And I'm going to really push this notion. Listen, when you are dealing with infinite series, every time sine or cosine show up, pretty much 99.9% of the time, you need to remember its absolute value is less than or equal to 1, period, end of story. It does not matter what goes into it. That inequality will hold always. And that generally takes you through everything involved every time they show up. So, because you can make a nice inequality with its absolute value being less than 1, you might want to set it up with the comparison test, the direct comparison test desk. Now, if you notice you have a square root involved with a bunch of addition, subtraction, it's getting kind of a lot of addition, subtractions. Limit comparison test is going to be far easier to cope with than the direct comparison test. But, if you use the table and it works for you, great. But I'm just giving you an idea of where to head depending on what you're coping with. Then, once they deal with those comparison tests, they still have to come over and figure out if they are harmonic series, geometric, or p-series, and leave with a ticket for you have gained entrance to Club Converge, or exit, goodbye, don't bother at another desk. They will give you the same ticket. Now, if you get lost, don't forget you rushed the door while the nth term test for divergence was at the bathroom. Don't forget. Take a little look at your formula. If it heads to 0, keep looking. But if it does not head to 0, the term itself does not head to 0, that means you're adding something substantial forever, and you are heading to infinity. Go to the nth term test for divergence. It'll show you your way out, and maybe it'll be a place where it's not as embarrassing to exit. Maybe there's a lot of paparazzi at the exit waiting to take your picture, but not at the front. I don't know. Weird things go through my head. I can't explain why. So, now, I want to point out to you what isn't part of this bunch. And that is, you've got alternating series test, which usually you see, you've got that -1 to the n going on, or -1 to the n plus 1. That's a big indicator to head over to alternating series test. And notice it's close to the door of the nth term test for divergence. Yes, I am recording. Notice alternating series test is close to the door where they can head back over here to the nth term test for divergence and just kind of skirt out like, I'm sorry, I realize I probably should have been stopped by the nth term test for divergence from even entering. Yes, I did come in when they were at the bathroom. Okay, I'm out. Then what is left here? Ratio test. If you notice, multiplication, division is all you have going on with a bunch of formulas, there's a good chance ratio test is going to help you. But keep in mind, if you get equals 1, you need to head over most likely to the Muggle or mixed blood entrance to have a comparison test help you out to figure out which of these you should head toward. And by the way, harmonic series, that could be thrown into the p-series mix and not be needed at all. If this one took a bathroom break, there wouldn't be any problems. Now, all that's left. Did I mention the factorial? Real quick. Or a factorial. If you see a factorial hanging on, go to ratio test. Go directly to ratio test. Do not pass. Go. Or do not pass nth term test for divergence. I don't know. Whatever. The only thing left at this point is integral test. And I have these two wandering functions or wandering infinite series who are like, I'm not sure where to go. And they are kind of looking, in my head, I've got these little eyeballs that are going back and forth between integral test, or should I go over to the mixed entrance? Then it looks back at integral test, goes, ew, and then looks back at the mixed entrance and goes, can I compare myself to anyone? Try hard. And if it doesn't work out, then you're going to be forced to head over to integral test. Primarily, you're going to notice that when you have a natural log involved or an inverse tangent involved, that there's a good chance you may need to head to the integral test, But if you can find a way, this is going to be your better area if you can use the direct comparison test, like how sine and cosine, they're easy. These aren't always easy. But anyway, that is how to gain entrance to Club Convergence or go out the exit in despair and be humiliated by the paparazzi taking pictures on the outside, or let the person at the door actually take a check before you go around to everyone. So I'm going to leave that with you. I will post this. By the way, I want to add like little music things coming out of Club Converge, you know, because it's like everybody wants to go into Club Converge. It's playing some good music. Woo! Anyway, never mind. Over here, error. Now I need to talk to you more about understanding error. I'm going to start back with the alternating series error real quick. And I'm going to probably continue videotaping once class is over. Videotaping, isn't that old-fashioned? Recording. I'm going to continue recording when class is over, and I'm going to go through all of the examples with Lagrange error and alternating series error, and then make sure you're very clear on the other two errors before you go away for your weekend. And just a reminder, there are no quizzes, no tests until next week on Tuesday and Wednesday. We've still got Monday to try and get all of this taken care of. There is a practice test posted on Google Classroom. Now, a reminder, when you have an alternating series that passes the alternating series test, when you have the sum of the first so many terms, say the sum of the first 5 terms, the actual error of that partial sum is this distance, whatever it may be, and S represents the actual sum. The next term you were going to use, the absolute value of it, gives you a distance that is for sure larger than the actual error. So the error of the sum of the first 5 terms is no more than the absolute value of the 6th term, or the n plus 1 if you're using n's. So I'm going to go back to examples of that, but make sure you remember before I go on to the next thing, you really want to make sure to clearly state these things. You are dealing with an alternating series, and that's understood to be back and forth with positive, negative terms. If the absolute value of those terms decrease to 0, then you have an alternating series that passes the alternating series test. If that is your situation, the error is no more than the absolute value of the first omitted term, period. All right, now moving on to the other error, and I'm going to spend a bunch of time on this, and then probably class will be over before I go back to alternating series test, but again, you can watch the video later. So, Lagrange error. I'm going to step back and a little bit and go again with what I talked about yesterday. Make sure you're really clear. The remainder is the error. And the remainder is, if I absolute value it is the difference between the function with a particular number plugged into its x, the difference between that and a polynomial of a particular degree that it is supposed to be mimicked by, with that same b plugged in. And often the AP test will present you with this type of expression to mean error. Subtraction order doesn't matter. you want to pay attention to the n. And you're going to go n plus 1 on it. And it's really valuable for you to notice that this is the Taylor inequality. And that inequality is very, very, very similar to the Taylor formula. So, a quick reminder of the Taylor formula. Nth derivative at the center over n factorial times x minus the center to the n power. Now, what's the difference between this formula and working with the Taylor inequality, which leads to the Lagrange error? Well, number one, they one up the n's, which really doesn't make a different formula. But I'm going to show, let's one up the n's. And other than that, I'm not changing the formula. So really, it's not changing the formula. It's just an emphasis on whatever n you left off with, go one up from there. Go to the next one. Very similar to the alternating series error, except not as exact, not as specific and easy to deal with. Now, from there, the only thing different, I repeat, the only thing different is that. And we usually use the letter Z and express that we need to maximize the absolute value of this for some Z, but we don't know exactly what Z. The only thing we know is that the Z is somewhere between the center and the X we are approximating with. And I like to call that X a B, just to not have it just be a simple X. So that's actually an additional thing that's a little bit different, is that we already have a specific number to go in here. And that needs to be the number we're plugging into X in the polynomial to approximate for. So with that said, what I want you to realize is this turns into a slightly simpler formula for you to momentarily look at. This is a slightly simpler formula. In this formula, you want to keep in mind that you need to maximize something, but not worry yet what it is you need to maximize. For this formula, you need to figure out what is the B number that they are telling you to approximate the polynomial at. What is the center? What is the n? And when you use that, that spells out ban, but if you go backward, it spells out nab. Like I need to nab those numbers. So I'm going to go with nab because, or you can go with ban. It doesn't really matter. When you realize you need to deal with a Lagrange error, start with nab. You need to figure out what is the n, what is the degree of the polynomial you're approximating with, what is the a, what is the center of the polynomial, and then what is the b, the number you are approximating with to replace x. Find those three things, because once you find those three things, you can begin writing just maximize something over. And then keep in mind your Taylor formula. And normally your Taylor formula says n factorial, but we're going to one-up it. And normally your Taylor formula says x minus a to the n, but we're going to one-up it. And we're going to plug specifically b in. If you throw those numbers in there, you have a beginning. Then after you throw those numbers in, go back to, I need to maximize something. What is it that I need to maximize? And then you want to think, okay, I need to maximize whatever the n plus 1th derivative is with whatever crazy information is thrown at me. And I want to maximize what this could be for any z between a and b. Now, once you know a and b, you can make a nice little inequality out of them. That's okay. Let me do a little better job on showing that clearly. That was supposed to be something is less than or equal to z, which is less than or equal to something else. And depending on the order, it's either a and b, or it's b and a. If you write that much, you are likely to get half the credit so far of the credit you would be getting for your Lagrange error. Most of the time on free response, it's about 2 points. 1 point for getting the formula going, and then another point for actually getting it all the way through. I can't guarantee you that's what it's going to be, but I will say that most likely that's what it's going to be. So if you can at least write that much, that can get you going. And I'm going to now show you 3 examples that have shown up on the AP test of some very, very different situations, and talk to you about what the AP test is expecting out of you and how you go about this problem. So we talked about this one yesterday, and because of that, I'm going to do that problem last, and I'm going to move on and get the problems we haven't talked about yet out of the way. And I'm going to quickly just turn to the part where it says Lagrange error. And I'll point out to you that this is the 2008 exam. At that time, the first 3 questions were allowed a calculator. Now you only get the first 2 questions with a calculator. And let me warn you that there's no way your infinite series problem is going to be in the calculator section. With that said, let's take a look. Lagrange error shows up. Use the Lagrange error bound to show that, and let's start highlighting, the 3rd degree Taylor polynomial for h about x equals 2 approximates h of 1.9, and you need to show that it's with an error less than that number. I highlighted in blue your nab. So you're going to read through the problem and you're going to figure out what to nab for what is the degree of the polynomial you are using to approximate with. You are using a 3rd degree Taylor polynomial. Then what is the center? And usually you're going to see that all over the place. The center, often phrased with about x equals. And then lastly, what is the b they're saying to approximate for? What are you plugging into x? And does everyone see that? You got it, 1.9. Once you have found those three things, don't worry about all the information. You can get the majority of this stuff done once you have gotten this far. So with n being 3, I'm going to 1-up it to 4, and 4 is going to be my focus. I need to figure out some maximum that I will come back to later. And then think about the Taylor formula. Normally you do divided by n factorial times x minus a to the n power. The a is 2. The x is the question, what am I plugging in to approximate 4? 1.9. And you've got a lot done at that point. Then you want to keep in mind, as you look at all these 4s, that you're trying to maximize. Now, normally what goes there is the nth derivative that matches these numbers. So fourth derivative, usually it's of x, or not of x, of a, the center. But instead, you're going to put a z. And then you're going to say, I need to find the largest possible absolute value. I need to maximize this, where z, the input, is somewhere between 1.9 and 2. This is where I need a laser pointer ability. I know there's some programs that use it, but anyway, moving on. So I'm going to, because of that, right here in inequality, 1.9 is smaller than 2. And so that is what I need to have for this maximum m. What did you do, you silly thing? Okay, let's try this again. I'm just erasing that. There we go. Then I'm going to lasso this so I can nicely place it right there. So the problem wanted you to express that the error is less than a certain amount. The absolute value of the error is expected to be smaller or equal to, I don't like writing or equal to because it's so ridiculous. And you need this to end up being less than that number that was there, which I already forgot, 3 times 10 to the negative 4. You are almost there. And all you have done when you have reached this point is you have nabbed your 3 numbers and remembered the formula that you are using. Now, we focus on this. Fourth derivative of the function. Oh, the function was h, so I should probably use h instead of f. That was the named function h. Fourth derivative of h. Here we go. I need information about the fourth derivative of h. Where do I have information about the fourth derivative of h? Look, seek, look, seek. Ooh, hey, look. Fourth derivative of h. It's a table. Oh my goodness, a chart. Yeah. So I've got x equals 1, 2, 3. And then what is it that matters about my fourth derivative? I am looking at where its input is between 1.9 and 2. Here's, however, a really key issue that the AP test likes to throw in with Lagrange error. And that's the issue of stay safe. What information do you actually have to work with and go with the largest possible number that is still safe within what the fourth derivative of this function could possibly be between 1.9 and 2. Exactly. You want to realize that the interval between 1.9 and 2 is in here, but you don't know 1.9, so you're going to have to go all the way over to 1. And you're going to look at these values that you are aware of. Now, I want to point something else out that's really kind of important that you might overlook and not even realize it mattered. If you know that the fourth derivative of h is increasing, then it's not going to have some relative maximum occur between x equals 1 and x equals 2 that you're not aware of by this chart. In fact, it means your largest value is at 2. But just realize that that is something that matters when it comes to tables, is the fact that you know for sure you're not having any hidden highs or lows in between 1 and 2. That does need to be there. So what do we have? We have used that. 584 divided by 9. So now I'm going to come back. 584 divided by 9 is going to replace that highlight, and now I can say that the absolute value of the error is less than that divided by 4 factorial times, now 1.9 minus 2, no biggie, negative 0.1 to the fourth power. And that negative sign is going to be fourth powered away, so no big deal. And if you have enough confidence in yourself, you can just stop there, call it a day. You've got the full points. If you want to make sure that this is working, this problem allowed you a calculator, and you can take a look at what is this and make sure that it is smaller than 3 times 10 to the fourth, which it is. So that's what you would do with that particular Lagrange problem. Now I'm going to take you all the way back to 2004, where some of you were being born that year. A couple of you weren't born yet, and some of you were maybe turning 1. Aww. Anyway, part C. Use the Lagrange error bound. Now, soon as you see that, just go nab. I need to nab 3 numbers. What are they? I want to give you a moment. You nab them, find them, nab them. And Jacqueline, don't answer quickly. And I'm going to have to tell Taya to not answer quickly as well. You know, the sophomores. Joking. Mm-hmm. Keep looking. Yeah. And realize that you might get some of the information within Part C, but you may have to look earlier in the problem, things that have been told to you about the polynomial. So does everyone see the B right away? B is actually the easiest thing to see in this situation because it is saying what is the error, what is the difference when 1/10 is plugged in. Yep. Then you're looking for what's the center, what's the degree. It didn't tell you anything about the degree in the way it wrote it. But that P has to represent something that they told you what it was already. And so you need to look up higher and go, where did they tell me what P represents? And it's right here at the very beginning. It told you it was the third degree Taylor polynomial for F. So now you know you're using a degree 3 polynomial to approximate the F function. And then the last thing is, what is the center? And it tells it to you there. And honestly, it talks about it in some other places, like right there. But you really want to look more at the initial statements. We've got our nab. Now, write the inequality that goes with that nab. Start with, you need some maximum value divided by 1 up your n and go, divided by 4 factorial times an x minus a to the 4th power. The x minus a is really, in this situation, b minus a. And then from there, the thing you're trying to maximize is the 4th derivative of the function at some z, the absolute value of it. You are trying to maximize this value for a z that is between 0 and 1/10. And in order for me to write that clearly, I need to zoom in. And that is the formula that they're first looking for. And the problem said that they want you to show that this is less than 1 over 100. So if you want to make sure that you are writing down what is needing to be written down, I'm going to erase these for room. And I'm going to put what they said, the absolute value of f of 1/10 minus p of 1/10 is, now technically it is less than or equal to, but if you don't put the equal to, it should be fine. But when we max this out, we're going to be dealing with a less than. Now, let's focus on what is the largest we can get for our fourth derivative of f over this interval. What information am I given? Oh my goodness. Oh dear, oh dear, oh dear. For this problem, when you did part A and then further went on to part B, you had to do it by the most painful, brutal way of making that table of derivatives and then put the center in. And let me warn you big time. Do you see that if I plug 0 into that x, I am not getting the sign of 0. This is a shifted sine graph. It is a stretched and shifted, but what matters is it's shifted. This is not a sine graph where I am centered at a place of symmetry. Normally, when we have the graph of sine, we've got odd symmetry going on. And right at that center, the odd symmetry is working. And when that odd symmetry is working, we get only the odd exponents for our polynomial. But if I shift this, I have to get all the terms of my polynomial. And if I use the known Maclaurin series of sine x, I will not be able to find them and I will be completely incorrect. So that is a big, huge, very important warning. If you have a shifted sine or cosine, even if it says, hey, it's centered at x equals 0, this is no longer centered graphically the way that the Maclaurin series is. And you have to start by scratch. So here we go. When you found p of x, you already had to make the whole table where you've got your n's, your nth derivative with respect to x, and then you plug the center in. But right now, we're not concerned about the center, just the derivatives. So we're starting with the function sine of 5x plus pi over 4. And then we get to have some fun. 1, 2, 3, 4. Derivatives away! So derivative sine is cosine of blah times the derivative of that blah, which is going to be a 5, and I'm going to save us a little bit of time by not writing that in, although it should be on a test. Then I take the derivative again. I have my constant multiple 5 from above. Then derivative cosine is negative sine of blah, and the derivative of blah is another 5. Then when I go to the third derivative, I'm starting off with negative 25. And then I take the derivative of sine, and I get cosine of blah times the derivative of blah, which is an extra times 5. And then I take the derivative one more time. I already have, I'm just going to change this to, I've got 5 to the third power at the moment. And it's negative 5 to the third power for all of this. I take the derivative of cosine, and I get negative sine of blah times the derivative of blah, which is 5. And then I'm going to put in that that is 5x plus pi over 4, and that was what was in the parentheses for each of those. You had to go through all of that to get to this point. Now, you're going to need to listen to what I'm about to say. I'm writing this down at the moment, and then I'm going to say something that is extremely important for you to pay attention to. Okay, you are expected to deal with z, where z is somewhere between 0 and 1/10. You don't have a calculator. I repeat, you do not have a calculator. Do you think you are expected to actually look at 1/10, plug it in, and figure out exactly what you're working with? In fact, if you do, you plug it in and you go, hey, that's 1/2. Maybe we're not doing too bad. What angle is 1/2 plus pi over 4? Do you know what angle that is on the unit circle? No, you don't. So really listen right now. Listen, 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 listen. Earlier, I talked about the fact that if sine and cosine, and I said it when I was showing you Club Converge, when sine and cosine show up, when you are dealing with infinite series, 99.9% of the time, Maybe it's a smaller percentage. I could be wrong, but most of the time you need to remember that when you see it show up, you're expected to know that the sign of it doesn't matter what I put in has an absolute value that is less than or equal to 1 every single time, no matter what you plug in, no matter what goes in, no matter what kind of a crazy function that is. That result will be less than or equal to 1 in its absolute value. That means you are allowed to say that the fourth derivative at z must be less than, and if you want, you can put equal to 5 to the fourth power. And just for the sake of it, I'm going to put times 1 to emphasize, and I should also do this. Absolute value bar, absolute value bar. There we go. Now we're good. The absolute value of sine of anything is less than or equal to 1. And I've got to say that this isn't going to give you an equal to 1. With that, you can then use 5 to the fourth power where this highlight is. So it is for sure less than 5 to the fourth power divided by 4 factorial times 1/10 to the fourth power. And you were expected to show that that was less than something. We need to now write down what that was. 1 over 100. Done. Now, if you have time and it really bugs you, you can take a look at 5 to the fourth over 4 factorial times 10 to the fourth power in the denominator, and you can make sure for yourself that that is going to be something less than 1 over 100. But realize without a calculator, they're expecting that there are some shortcuts you can take, such as, I've got 5 to the fourth divided by 10 to the fourth. What's that going to turn into? 5 divided by 10 to the fourth. It is 2 to the fourth in the denominator. Let me clean that up. This is what we have. And now the real question is 4 times 3 times 2, hey, let's bring those together, to the fifth power, going to be greater than 100. And you can start off with, yeah. And then whatever point you reach, yeah, that works, you know you're good. So I want to say again, when you are dealing with Lagrange error on the AP exam, you're looking for go big on maximizing that n plus 1th derivative. They might give you a table. Go with the largest possible thing in that table, but keep in mind some subtleties. Then they might force you to deal with actually taking that n plus 1th derivative of a function. Another thing, you might have a formula that involves sine or cosine. If your n plus 1th derivative involves sine or cosine within its formula, automatically throw absolute value bars around it, say less than or equal to 1, and move on. And don't bother anymore with sine and cosine. And then there's also this one that I really like, but I don't necessarily like the twist they have on it because I like to be a little more exact. But had to deal with it. So now I'm going to talk about this problem, and we still have 9 minutes of class. Tell me if I'm wrong. I think that's what we have left. But again, tell me if I'm wrong, please. Okay. For part D, you are told P4 is the fourth degree Taylor polynomial. Okay, it might, oh. Okay. Thank you. 3 minutes. I'm just going to keep going. Once it hits time, you are allowed to go. However, you can stick around and keep learning before your fourth period starts. But once it's fourth period time, I'm going to tell you, get out of here, go to your fourth period. And if you stay, you're going to have to tell me you don't have a fourth period. Okay, here we go. So we have this statement. And there's a lot in that statement. Remember that the first thing you're looking for with Lagrange error is nab3 numbers. While they did make sure to clarify that this is the fourth degree polynomial, that sub number on the name of a polynomial generally is expressing the degree of the polynomial. The B is noticeable. It's the number we're plugging in. And then A, you're just looking for something like, oh, say Taylor polynomial about x equals 0. You've got your center. So with that nab information, I'm going to be thinking about my Taylor formula. I'm going to 1-up my n. And I'm going to focus on that 5. And I'm going to remember that the typical Taylor formula goes that nth derivative at a center, but we're not going to go with the center, divided by that number factorial times x minus a to that power. And then the x is your b, the a is your center. So 1/4 minus 0. And you do need to absolute value the whole thing. And this kind of takes it if you just throw that on. So let's get started with, they specifically said to show an inequality, so let's start writing exactly that inequality. P4 of 1/4 minus f of 1/4 absolute values. It is less than or equal to, sure, why not? And then as I'm looking at it, I'm seeing I don't need to absolute value the 5 factorial. And then I've got 1/4 to the 5th power. And then I need to find out what is the maximum that I can get out of the absolute value of my 5th derivative at z, where z is a number somewhere between the center and the x I'm plugging in. The center is 0, the x I'm plugging in is 1/4. That's my a and b of nab. 0 and 1/4. And it's best to put an absolute value around that. Now, you're almost done. The focus is maximizing 5th derivative. Z is between 0 and 1/4. The information I'm given is the graph of the absolute value of the 5th derivative. Whoa, who knew they would give us exactly what we needed? Now, between 0 and 1/4, that's this x interval. But pay attention really carefully to my explanation of what the AP test expects of you. You need to be positive of a number that is at least the maximum, if not greater than the maximum possible, of the fifth derivative between 0 and 1/4. And you want to notice that at 1/4, it's cutting through at a y value that you are not entirely certain of. You could make a guess, and that could be problematic. The AP test expects you to put down a number that is for sure going to work. You know, maybe you feel like, how about 39? But you know, why would you want to have to multiply things by 39 when you've got 40 right there? Hey, you have to use something where it is extraordinarily clear through the information given that it stays under that number while it travels from 0 to 1/4. You need to use the 40. Always go big. The moral of the story is, for this maximum value, go big. That was 40. So now I know I am less than, and then 40 replaces the maximum value there. 5 factorial, 1/4 to the 5th power. And then I need to make sure that I finish the inequality, and state that it is less than 3,000, 1 over 3,000. Now, once you reach this point, you can stop. You don't need to make sure that this is the inequality that you think it is. But if you want to know that they have this set up where you can, usually this is something that isn't too hard to play with. If I play with this number, I can start simplifying it pretty quickly with a little bit of logic. So I can take away one of these and divide by 4, and now I'm just dealing with 10. Then I can remember 5 factorial is 5 times 4 times 3 times 2, and then I additionally have times a 4 to the 4th power and a 10, and then suddenly go, whoa, hey, 5 times 2 is 10, and very, very quickly you've narrowed down that number that you actually got. And now if you take a look at it, it is 1 over 3 times, and actually 4 to the 5th power. And how comfortable do you feel with saying that that is less than 1 over 3,000? And I certainly see the quick eh. And if I look at the denominators, I need 4 to the 5th to be something that is larger than 1,000. And without a calculator, you should be able to at least contemplate a bit and come to a realization that that inequality is going to work. You do not have to show that you know the inequality works. This is something you may want to do on the scratch paper of the AP test. All you have to write is this. Now, as promised, I'm going to go back over to the alternating series test problems and go through those and talk about the alternating series test. And let me see. I think I had gone through this problem with you yesterday, so I'm going to do that one last. And I'm going to start here with the 2017 problem that is here. And I'm going to skip down to where the error occurs, keeping in mind that there was a lot of stuff that was already done on this free response problem. And This just definitely captures my eye as to error, error, error. And then on top of that, it says use the alternating series error bound to show that this is true. So that emphasizes, hey, it's an alternating series. Use it. Now, what we actually want to take a look at is what do we have going into this? What is our P sub 4 polynomial? And in part A, you are expected to show that this is the polynomial you get for f. Then it went on to change that f to a g by integrating that f. And g is the function that we are focused on alternating series error with. And what I'm going to do is I'm just going to grab the answer to C from the 2017 exam and bring it over to save us the time of that part. Just give me a second and I'm going to have that for you. And snip. And by the way, if you do have a fourth period, you should go so that you can get into that meet for your fourth period. Those of you that are here do not have fourth period classes. Okay. So this is G. Or this is approximating, I should say. Oh, wait. I can do straight equal signs because I've got plus dot, dot, dot after the formula. All right, here we go. It's asking you to show that the error of the fourth degree polynomial with 1/2 plugged into the x's is less than 1 over 500. Well, what's going to be the first omitted term? Ding, 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 with 1/2 plugged in. So for a quick explanation, your error is found by taking the absolute value of negative x to the 5th over 20, plugging in 1/2. That's what your next term was going to be. That's your error. Now, you are expected to express this in the right way. So what you need to do is express that Pn of x is an alternating series. Even though they told you, just restate it, because this is you telling them, I know this is necessary to come to the conclusion I'm about to come to. Pn of x is an alternating series. The absolute value of its terms decrease to 0. In other words, this is an alternating series that passes the alternating series test. Then the error is no more than the first omitted term. And it's best to restate that they said P4 of 1/2 minus G of 1/2, which you know is the error, must be less than the absolute value of that negative 1/2 to the 5th power over 20. And then you can say less than 1 over 500, and that is full credit. You can absolute value the negative sign away if you like, and then write what that turns into, but do that on scratch paper because you have full credit right here. And if you make an error in simplifying, you lost that credit. So put it on scratch paper if you feel the need to double check that this is true. And from there, I'm going to leave it and I'm going to move on to another problem. Oh, wait, that was the last problem on my list, wasn't it? Oh, I only had 2 with alternating series error. Got it. So back to this problem, which we talked about yesterday, but I want to go through it again. So in part C, you are told that you have P4, it's a 4th degree Taylor polynomial. And it even says use alternating series error to find an upper bound. Now here it's not giving you a show that it's less than this number. It's just saying find an upper bound. And I want to warn you that they're not necessarily going to tell you to use the alternating series error bound or to tell you to use the Lagrange error bound. If you are not told which one to use, first ask yourself, is this series a converging alternating series that passes the alternating series test? It must have the absolute value of its terms decrease to 0, or you cannot use the alternating series error bound. And that's when you're going to turn to the Lagrange error bound. And I would advise that you state which error test you are using when it doesn't tell you which one to use. So here we go with what we are working on. It said to use 4th degree polynomial with 2 plugged in. So that means you're going to look at your P polynomial, which we had found that this is my P polynomial. This is the formula. The degree 4 polynomial is made up by adding those 3 together with 2 plugged in. The very next term is negative x to the 5th over 4 times 3 to the 4th power. And again, you're plugging 2 into the x. Absolute value, there's your upper bound. But make sure that you express all the things that need to be expressed, because they're going to be expecting you to say something like, I recognize that Pn of x is an alternating series. I also recognize that the absolute value of its terms decrease to 0. Therefore, the error is no more than the first omitted term. And then look back at what they expressed and rewrite what they expressed. They said absolute value P4 of 2 minus F of 2. And you just need to express that is less than that number. You do not have to simplify that number. You can leave it there as is and call it a day. So you can see that the alternating series error is much easier to use than the Lagrange error. Keep in mind with the Lagrange error that the big issue is go big on that n+1th derivative. And other than that, you just have to nab your nab, NAB, the degree of the polynomial you are approximating with, A, the center, B, the x you're approximating at. That is all, and I will try to make some more videos for homework 28 to help you out on those really challenging problems. And now it's just a matter of trying to figure out